Hello, this is Vishvaa here, and I am going to do a live demonstration of the 12th problem of the IUPT 2024 problem soap spiral. Let's get started with the things required to do this experiment. Let's understand the basics of two main concepts required to explain this phenomenon. The first is surface tension. Surface tension is the property of the free surface of the liquid due to which it behaves like a stretched rubber sheet in state of tension. We can understand the origin of surface tension with a cup filled with water like this. Let's consider two molecules, one at the surface of the liquid and another well inside the surface. If we consider a molecule well inside the surface, it experiences cohesive forces in all directions and all the particles surrounding it are identical, but at the surface it does not have identical particles surrounding it, due to which it experiences a net inward force, creating a surface tension. Let's see the unique properties about water surface tension. Due to the hydrogen bonds between the water molecules, it resists the surface from breaking or stretching. It gives rise to a higher surface tension compared to the liquids. Understand the second basic concept, that is the minimal area theory, generally known as the plateau's problem. So after a soap film comes in equilibrium, it tries to acquire a state of minimum energy. So this can be attained only when the surface area is minimum. Carrying out the area minimization of a film using the Euler-Lagrange equation will result in a non-linear partial differential equation known as Lagrange equation, which all minimal surfaces must satisfy. Okay, let's dip the slinky inside the bubble solution and take it out. So after dipping the slinky inside the bubble solution, the soap molecules get stuck on the surface of the slinky due to adhesive forces of contact. You can see the molecules getting stuck on the surface of the slinky. After taking it out, we can see the soap film being formed between the slinky. Let's understand this. So now the soap molecules are in contact with the surfaces of the coils of the slinky. When we try to extend it, you can see that the soap molecules remain in contact with the coil of the slinky because due to the adhesive forces, thus creating a film between the coils of the slinky, thus creating a film. So if we try to extend it more and more and more, at some point it breaks. So let's understand the shape of this film. So we can understand the shape of the soap film formed between the coils of the slinky by considering four distinct distances between the coils of the slinky when stretched. First, let's consider the distance is very less. In this case, the shape of the soap film is like the curved surface area of a cylinder with negligible thickness. If we increase the distance further, then the curved surface area dips in towards the central axis, thus forming a shape which is also known as the catenoid shape. There comes a critical point after which, if we increase the distance, this catenoid shape breaks and it forms two discs of film between the coils of the slinky. So let's start the experiment now. So we have dipped in the slinky inside the bubble solution, and if we extend it, you can see the soap film forming between the layers of the slinky. And if we try to disturb the film at the bottommost layer, let's see what happens. You can see that the surface of the film is disturbed till the topmost point. So let's start the experiment now. So we have dipped in the slinky inside the bubble solution, and if we extend it, you can see the soap film forming between the layers of the slinky. And if we try to disturb the film at the bottommost layer, let's see what happens. You can see that the surface of the film is disturbed till the topmost point. Now let's see a possible explanation of the outcome. Consider a thin soap film and let's poke a hole inside it. Consider the particles surrounding that hole. Initially they were in equilibrium with net force 0 acting on them, but after we poke the hole, the net force acts on them in the radially outward direction due to surface tension, thus giving them a velocity and momentum. So after the particles gain the velocity, let's see here, they move radially outwards from this hole and they move towards the next film which is above them. The particles on that film are stationary initially, so this goes and collides with the molecules of the next film. Let's see the collision between these two particles, one which is moving with the velocity v and another which is stationary. If this particle hits that Then this particles comes to rest and the other particles travels with the velocity v dash. This is v dash because momentum is not conserved here. This is due to forces acting on them. Momentum can be conserved only when the net force acting on the system is zero. Gravity is acting on them, so it moves the velocity. In this molecules which is traveling with the velocity v dash collides with the particles of the next film, giving them velocity, and this goes on. Another point which we can note in this experiment is that if we pop out the surface of the bottommost film, then it goes on till the top, but the rate at which it goes is uniform between two adjacent films. So this is what my explanation for this problem is. So this is what I felt could be the possible explanation of this problem, soap spiral. Thank you.